we're going to talk a little bit about the sampling distribution of a proportion, the sample proportion. So first we're going to take a look at some graphs or some histograms. We're looking at the binomial distribution, which remember we have an N and a P. N represents the number of trials, and P equals the probability of success. In other words, we had a constant probability of success. Just like an example for this is P is 0.5, that'd be like flipping a coin 10 times. And we would observe the number of heads that we achieved. So in this case, this is 5 heads, this is 6 heads, 7 heads, 8 heads, 9 heads, and 10 heads does occur. The probability is just so small it doesn't show up here. So one thing to recognize here that the close relationship between the binomial distribution and the sample proportion, which we call p hat. P hat is just the proportion of your sample that is a success. So in this case, if 6 out of the 10 were successes, then 6 divided by 10 is 0.6. That's my p hat when you get 6 successes. You can notice that the most probable p hat is 0.5. That's this 5 out of the 10. So what we're going to look here is what happens when P is not 0.5. First is what we're going to look at. So here's 0.4. Notice that we're centered around 4 successes, which is P hat equals P4, or P hat is equal to 0.4. Notice that this distribution starts looking a little skewed to the right. If we shift, this was 0.2. Notice that the most probable is 2 successes, which would be P hat is 0.2. And we're more right skewed here. Okay, so one thing to notice is when P is further away from 0.5, at least in this direction, it's becoming more skewed. And also that it's centered around the population proportion. In other words, our probability of success. So we'll look at 0.1 gets more right skewed, centered around 1. So I'll go back the other way, higher than 0.6. And as you may have guessed, these are going to get left skewed. Okay, so the further you get to away from 0.5 for P, the more skewed it's going to be in one direction. The higher the value of P, the more left skewed it's going to be, and the lower the value of P, the more right skewed it's going to be. So now we're going to look at what happens when N gets larger. So in other words, since we're going to set the parameter at a fairly extreme value, P is going to be 0.1 for us, so 10% chance of success. We're going to see what happens when N increases. So when we went into N equals 20, we're still right skewed. Perhaps maybe less right skewed than it was when we were N equals 10. Notice here we have an extreme value of P equals 0.1. But when N got larger, N equals 40, it becomes less skewed. It's becoming more normal. And as you can see, as N equals 80, it becomes even more normal. So that's N equals 60, but went back, I guess I put those in opposite order there. But you can see as larger N gets, the more normal it gets. Okay, so let's look at these two formulas and understand what they mean. We noticed that our histogram was always centered around the population proportion. And that's basically what this is saying. The mean of all of the sample proportions is equal to the population proportion. And the standard deviation of all the sample proportions is equal to this. The square root of P times 1 minus P, which sometimes we'll call Q, divided by N. Okay? So another thing that we'll talk about here, and I'll demonstrate this here, to check for the normal sampling distribution for proportions, we want to check that NP and NQ are both greater than or equal to 10. So if we're looking at, let's say N equals 5. Well, let's go bigger than that. Let's go N equals 20. And P equals 0.5. So remember that 0.5 is basically the best value that you can have as far as being normal. The further we get away from 0.5 for P, the harder it was to be normal. So In this case, if P is 0.5, then also Q is 0.5. Q is the complement of success, which is a failure. This is the probability of failure. If there's a 50% chance of flipping a heads, there's a 50% chance of not flipping a heads or flipping a tails. So in this case, you have 20 times 0.5 is 10, and 20 times 0.5 is 10. So if you're looking at this combination of N and P, that would be approximately normally distributed, because both NP and Q are at least 10. Now if we had, stick the same, just to illustrate this one time, if N equals 20, and P equals 0.8, then it might be easier to say, yeah, 20 times 0.8, that's 16. That is bigger than 10. But if P is large, then that means Q is small. And that goes the opposite. If P is small, then Q is big. Okay, so Q is 0.2 here. And 20 times 0.2 is 4. So then that does not satisfy this condition. We need both NP and NQ to be at least 10. So that's what we'll check to see if the sampling distribution for the sample proportion is approximately normal. So I'm going to look at an example here. It says television executives and companies who advertise on TV are interested in how many viewers watch particular television shows. According to 2001 Nielsen ratings, Survivor 2 was one of the most watched television shows in the U.S. during every week that it was aired. Okay. So suppose that the true proportion of U.S. adults who watch Survivor 2 is 0.37. Suppose we did a survey with N equals 100. In other words, we're going to sample 100 people, and we're going to find the proportion of those 100 people who watched it. So if 37 people out of that 100 people watched, then our P hat would be 0.37. If 40 out of those 100 people watched, then our P hat would be 0.4. So it says, suppose we're going to do this 1,000 times. Now that number is really not important to us. We just need to do it enough times to get an idea of what the shape of this distribution is. The P and N is really what we're concerned with here. So we could do a check here to see if we thought it was going to be approximately normally distributed. P is 0.37. Q is 0.63. That's the complement of 0.37. And if you multiply those by 100, you get 37 and 63. And both of those are greater than 10. So it should be approximately normally distributed. We look at the sampling distribution, and we see that it is approximately normally distributed. We have noticed that the mean, or I guess the center, it is the mean, but right now I'll call it the center. The center of this histogram or distribution is right around the true population proportion. So all of these values represents sampling 100 people and getting 37 of those 100 people watch Survivor. These group, they sampled 100 people, and 52 out of those 100 people watched it. And remember, we're assuming here that the true population proportion is 0.37. So now we're going to look at an example, which is going to lead us into a hypothesis test for proportions. It said, what if, like most times, we don't know the true proportion of U.S. adults who watched Survivor 2, but its producers claimed it was 0.37. However, we sampled 100 people and found that 20 of these people watched. Is this evidence against the producer's claims? This is what we're going to be asked to do a lot of times. That's a hypothesis test. So let's take a look at this. So let's say first we did our HO here, which we're getting into hypothesis test a little bit here. Is that the true proportion is 0.37. And our HA, now it didn't say whether we thought that let me check, that we thought that value was lower than 0.37. We just think that, well, let me make sure we didn't say that. Okay. Yeah, it just says claim against this value. So it doesn't say that we think that it's actually lower than 0.37 or greater than 0.37. We just think, we're just trying to get evidence that it's not 0.37. Okay, now embedded in the question, which will tell you whether you're trying to test well less than or greater than or not equals. This is a two-sided test because we're testing any evidence against 0.37. So we're normally going to have to check some conditions here, but I'm going to bypass those just to get an idea of how we use the sampling distribution. So what we're doing here is it'll say, in a hypothesis test, we assume that the null hypothesis is true. Until we get evidence otherwise, we assume that the null hypothesis is true. So this distribution is centered around 0.37. Now we actually already did the check to see if this is one of the conditions, is that the sampling distribution is approximately normal. But if we're assuming that P is 0.37 and we tested 100 people, then that's 0.37 times 100 and 0.63 times 100. Both of those, again, are greater than 10. So this is going to be approximately normal. Okay, it's centered around 0.37 because remember that we know that the mean of all of these p hats is p. We also know that the standard deviation of these p hats is p q n. Okay, so we can get an idea of what the standard deviation of this is. That is 0.37 times 0.63 divided by 100. So let's take a look at what our standard deviation is. So we have the square root of 0.37 times 0.63 divided by 100. And I don't have to be careful of, well, I guess we do have to be careful, but it's fine not to put parentheses here because order of operations will do multiplicate, will do inside the radical first. It'll do multiplication, that times that first, and then divide that by 100. So we're fine here. This is what our standard deviation is. So I'll round this to, let's say, 4 decimal places. 0, 4, 8, 3. And the reason I'm rounding that to 4 decimal places is because we're dealing with a proportion. So all of our numbers are going to be decimals. There's a big difference between 10% and 20%, which is only 1 decimal place. So we just go further out in decimals when you're working with percentages or proportions. So we have here our standard deviation. Now, the problem said that we sampled 100 people, and 20 of them actually watched Survivor. So that's a p hat of 0.2. Now notice that this normal distribution is each one of these values in here represents a p hat. It represents us sampling 100 people. If the true proportion really is 0.37, then what we would get. Okay, so to get evidence against this, we're going to find out this probability. And because we're doing a does not equals test, we're actually going to multiply it by 2 because we're not just testing that as less than, we're also testing it, even if we got greater than, that would be evidence against that claim. So we're trying to find out how likely is this? So what we're going to do is get a z-score. How many standard deviations above the mean, or I guess below the mean this time, is 0.2? And then we're going to get an idea how likely that is by using a normal CDF or either using a table. I'll use normal CDF. So we'll get this value. We have 0.2 minus 0.37. And we're going to divide that by 0.0483. Now, that's our z-score, and we know that that's a pretty extreme z-score. 3.5 standard deviations below the mean. So we can get an idea how likely that is by going to normal CDF. We're trying to get this percentage. So our lower bound is negative infinity, way out here. Our upper bound is our z-score that we just found, which is our previous answer, which was negative 3.5. Our mean is 0 and our standard deviation is 1 if we're working with z-scores. We paste that and we get that probability. Now that's the probability of, if the true proportion really is 0.37, the probability that we get a sample proportion of 20% or 0.2 or less than that. Because we're doing a two-sided test, I can double that, or I need to double that. So I get this. And let me write this down and then talk about what it means again. So this is 0, 0, 0, 4, 3, 2. I'm going out several decimal places there. This is scientific notation, and e to the negative fourth means that you move your decimal place to the left 4 units. Now, what does this mean? This is what we call a p-value again. We mentioned this when we were working with the sampling distribution for the mean. And it says if the true proportion, population proportion, is really 0.37, like the producers of Survivor says that it was, you would only expect to get a sample proportion of 20% or more extreme. Now, when I say more extreme, I mean less than 0.2 or more than, let's see, what is this? There's 0.17 in between these two values, so if you go another 0.17, that would be 0.54 right here. So the probability of getting less than 0.2 or more than 0.54 is this right here, and that's a very small probability. So what do we gain by that? We say, well, the only thing that we've assumed in this problem was that p was 0.37, and the fact that that doesn't happen very often, it's unlikely to happen, that gives us evidence that the true population proportion really is not 0.37.